If we have a vector space and are just given one vector to start with, what can we do with it? Well, under the operation of scalar multiplication, we can scale the vector to create new vectors. We can scale it by +2 or -2 or any real scalar. And what we'll notice is that all of our resultant vectors lie along the same line that the original vector was on. Now, if we were given a second vector, we can apply both vector addition and scalar multiplication to make even more vectors. We'll place a mark on the tip of the outmost vector as to show where our resultant vector would be pointed. We can see that by combining vectors, we can create many new vectors all over the plane. Let's try this in writing. If we're combining vectors in linear algebra, then we're making linear combinations. A linear combination is any vector that can be written in the form alpha1 v1 plus alpha2 v2 and so on up to alpha n vn, where the v's are vectors in our set and alphas are real numbers. Let's look at this case where we have two vectors on the same line. We can write the second vector as a linear combination of the first vector. If the blue vector is 2, -1, and our red vector is -2, 1 based off their x and y coordinates, then we can see that the red vector is just the blue vector scaled by -1. We call this red vector linearly dependent. Now, if we have two different vectors, we can try to write out the red vector as a linear combination of the blue vector. The red vector is 0, 1, and the blue vector is 1, 0. But we may see a problem. If we distribute the scalar into this vector, then we have this tricky system of equations where we're saying alpha equals 0 and 1 equals 0. Here, we have a contradiction. There's no real value of alpha that we can use to make the red vector from the blue vector, so we can't write them as a linear combination. So we call this red vector linearly independent. So a vector is linearly dependent if that vector can be formed as a linear combination of other vectors in the set. And a vector is linearly independent if that vector cannot be formed as a linear combination of other vectors in the set. Now, instead of asking if a single vector is linearly dependent, we can look at a set of vectors and ask collectively, is there a vector in that set that can be written as a linear combination of the other vectors in that set? If there exists a vector inside the set that can be written as a linear combination of the others, then the set is linearly dependent. And if there doesn't exist such a vector, then the set is linearly independent. If we look at a set of vectors, we can check the linear dependence of the set. If we write out the equation 0 equals alpha1 v1 plus alpha2 v2 and so on, where v1 up to vn are in the set we want to test, and alpha1 to alpha n are real numbers, if this equation admits a real solution, then there exists a vector in that set that can be formed as a linear combination of the other vectors in the set, and therefore the set is said to be linearly dependent. Now note, there exists a trivial solution where you just set all the scalars to 0, and of course in that case the equation works out, but obviously that doesn't determine the dependence of the set. So if there is no solution besides the trivial case, then no vector in that set can be formed as a linear combination of the other vectors, and therefore the set is said to be linearly independent. This approach is actually really intuitive. In the simplest case where we have two vectors on the same line, we know that one is a linear combination of the other, and we can see that they're linearly dependent as when we add them up, we get that 0 vector that we want. Now, if we have a set of vectors that is linearly dependent, we can add them and scale them so that they go back to the origin. Now think about it. Being linearly dependent means that a vector in the set can be written as a linear combination of the other vectors. So say that v4 can be written as a combination of v1, 2, and 3. If we throw a scalar out in front of v4, move it to the other side, then let the scalar absorb the negative sign, we're back to our equation where the linear combination equals 0. We can also do this in the opposite direction. We've got our equation that equals 0, and we know that one of the vectors is a linear combination. So we can move v4 to the other side, divide out the scalar, and then let it be absorbed into the other scalars, and we see our linear equation for v4. Trying this on the contrary, if we have a set of vectors that is linearly independent, it doesn't matter how we add or scale the vectors, we can't get back to the origin, as we don't have any real solutions. Except, of course, for that trivial case, where we multiply each vector by 0. So, is the set of vectors 1, 0, 3, 2, 2, 4, and 3, 4, 5 linearly dependent? Well, we can write out our equation and start trying to find a solution. In the second equation, we only have two variables since alpha 1 is multiplied by 0. So we can rearrange to get that alpha 2 is equal to negative 2 times alpha 3. Substituting that into the third equation, we can get an expression. Simplify it down, and we get that alpha 1 being equal to alpha 3. Substituting that into our first equation, all the alphas are going to cancel out, and we're left with 0 equals 0. Like that, we found our solution to the equation. Alpha 1 equals whatever alpha 3 equals, so we'll set them both to 1. And then alpha 2 equals negative 2 times alpha 3, so just negative 2. Since our equation has a real solution, these three vectors are linearly dependent. Something interesting is that the set containing only the 0 vector is linearly dependent as it passes our dependence test. If we write out our equation 0 equals alpha v, where v is just the 0 vector, then we can pick any real number alpha and our equation will be satisfied, since multiplying a scalar by 0 gets us back to 0. So since there exists a real solution to this equation, the set is linearly dependent. Better yet, any set containing the 0 vector is linearly dependent. We can go off what we just had before and just show that if we write out our dependence test, for all the other vectors in our set, we can just set their scalars equal to 0, and then set the scalar in front of the 0 vector to whatever we want, and we will still have the equation equal 0. So our equation has a real solution. Now that we understand linear combinations and linear dependence, the span of a set of vectors is the set of all the possible linear combinations. We denote span by a capital S and a subscript as the set of vectors that makes it up. If we have just one vector, then its span is all the vectors we can create through scaling that vector. So it's a line that passes through the vector. Unless, of course, it's the 0 vector, where we're just stuck to a point at the origin. If we have two vectors, then its span is all the vectors we can create through adding and scaling the vectors. So if the two vectors are linearly dependent, then we're still stuck on a line. But if the vectors are linearly independent, then we would have a plane where the vectors lie. We could take it up to 3 dimensions or 4 dimensions and keep going, but you get the idea. The span is a set of all the possible linear combinations that we can make from a set of vectors. If we're working in the vector space V, then a specific set of vectors is a subset of V. But if we take the span of a set of vectors, then we will always have a subspace of V. To prove that the span is always a subspace, we need to check that the 0 vector is in the span is closed under vector addition, and the span is closed under scalar multiplication. If we're given a set of vectors, then we can write out a linear combination that the 0 vector equals alpha 1 v1 plus alpha 2 v2, and so on. Now to prove that that 0 vector is in our span, we just set all the alphas equal to 0, and then our resultant vector is 0. Now, if we have two vectors in our span, and we want to prove that their sum is always in our span, we can say x is equal to alpha 1 v1 plus alpha 2 v2 and so on, where the scalars are alpha. Then we can do the same for y and call the scalars beta. Adding x and y, we get the addition of their linear combinations on the one side. Rearranging, we get alpha and beta out in front of every vector. And since alpha and beta are both real scalars, their sum is also a real scalar. So now we have an equation for the sum of x and y, and therefore the span is closed under vector addition. Proving scalar multiplication, if we have an equation for v, then we can scale v by a scalar lambda, and also scale the other side of the equation by that lambda. Now, out in front of each vector, we have the product of two real scalars, which is also a scalar. So now we have an equation for v times a scalar. The span is closed under scalar multiplication. Since all three properties hold, the span of vectors is a real vector subspace.